bromine react at high temperature to form iodine monobromide. This is a reaction which is shown the structure of the molecules, and this is the bond energy. Now, once you understand the logic, this is a very simple topic. All that you need to understand is that it's a very commonsensical approach. If you want to break something, you need energy. So, for example, let us say there's a chair that I want to break. Now, if I want to break a chair, I need energy to break the chair. So, similarly, when you are breaking the bonds, you will require energy to break the bonds. For example, in this case, of course, you should have some idea of the chemical bonding. Not very deep idea, but basic understanding of chemical bonding is required, is a prerequisite. For example, if I2 is there, so 2I would be bonded together. So I'll have to break the bond of these 2I. For breaking the bond, this is the energy which will be required. I will have to put that energy in the system. So that is why to break. And please notice that only one mole of I2 gas is being broken. So here I will be breaking 1 mole of iodine molecules. Here I'll be breaking 1 mole of bromine molecules. But here, if you see, I'll be breaking 2 moles of IBR, iodine monobromide. So what I'm trying to imply here is that you should be very clear about the coefficient here, because that coefficient would imply the number of moles which would be required. Because if you see here, it is bond energy in kilojoules per mole. It is per mole. So here I have to break 1 mole of iodine molecules. So I will be requiring 150 kilojoule per mole. So I haven't written kilojoule per mole. You can write it here. Then next I have to break 1 mole of bromine gas molecules. So for that I will require 193 kilojoules. So total, this is the amount of energy which I require to break the reactants. So to break the reactants, this is the amount of energy which I will require. I'll have to add that. So 3, 9, 5, 14, 1, 2, 3. 343 kilojoule per mole of energy I have to give in the system to break the bonds. Another example, if you want to take, if you have to break bones, if you want to break somebody's bones, you have to put in some energy to break the bones. So bones, bonds, same thing. Now when we come to the reactant side, the inverse would be taking place. Now what will be happening is there would be bond formation. 2 moles of iodine monobromide is being formed. 2 moles. Now, from these bond values can be used for breaking also, and when the bonds are made, this amount of energy is released. We just have to take care of the signs. So for example, in this case, the sign that we were using to break the bonds was positive. But when 2 moles of IBR would be formed, this amount of energy, 2 moles of IBR, this amount of energy would be released. So when 2 moles of IBR are formed, for 1 mole, 175 moles of energy. This is the sign that I'm using, because a negative energy implies that energy is released. You can imagine it like this. For example, this is the system. From this, energy is released, so the energy comes down. So to make when 2 iodine monobromide moles are made, 2 into 175 kilojoule per mole of energy is being released. So total energy which is being released is, this is the amount of energy that is being released. So this is the energy that is being released. This would be kilojoule per mole, but then this would be kilojoule. Similarly, this minus 175 is kilojoule per mole, but this is the energy, total energy which is now is leaving the system. So if you want to visualize, one way of visualizing this is that if this is the system, then the energy required to be put in the system would be 343 kilojoule, and then energy which will be released when the products are formed, the energy released would be 350 kilojoule. So minus 7 kilojoule, this would be the delta H. This is the amount of energy which is being released. This is the amount of energy which is being released. So this is a exothermic reaction. Exothermic reaction. This is the net energy being released. Remember, when delta H is negative, energy is released. You can imagine it like this is the amount of energy which is being given out from the system. And all the systems which give out energy, they are exothermic reaction. A typical example is a combustion reaction. So combustion reaction, energy is given out. So what we understand is that 343 kilojoule of energy is required to break the bonds, and 350 kilojoule is released from the system. So another way, if you want to visualize, if this is the system, then you will require 343 kilojoule. This energy would be required to break the bonds of the reactant side. You will first break the bonds. Then when the bonds are made, then 350 kilojoule. This is the amount of energy which the system would release when the products are formed. So the net energy which is released, because in this case the negative sign is more than the positive side. So we will see that 7 kilojoule is the amount of energy which the system would release. So our answer would be delta H would be minus 7. They are asking for the sign also. So our answer would be minus 7 kilojoule per mole, and energy required to break the bonds. To break the bonds, plus 343 kilojoule would be required, and total amount released is minus 350 kilojoule. So as I told you, it's this topic is fairly simple, and more or less one question would come from this topic. So let's do few more numericals. So let's look at the next numerical.